Alright, I'm going to show you how to calculate an equilibrium concentration given some initial values of substances and a equilibrium constant. To start, we need to have an equilibrium equation. So we have nitrogen and oxygen gas that are going to combine to form nitrogen monoxide. And of course, this needs to be balanced. We need to have these uh, equations so that we can write out our expression, which is going to be Kc equals products over reactants. So NO squared over N2 to the first and O2 to the first, where again I'm getting the powers from the coefficients of the balanced chemical equation. We need to create an ice table. We know we need an ice table because it says these two numbers are allowed to equilibrate, which means that they are not at equilibrium, so we can't use our equilibrium expression yet. So I'm going to set up my ice table. Again, I need I, C, and E for my initial change in concentration and equilibrium concentration. Put your substances from your equation up into your ice table. I like to separate my reactants from my products because, again, we use something a little bit different on the product side. And then it's good to put your coefficients in your ice table as well, because that's going to be the stoichiometric ratio at which these substances change. We can always include a 0 for our initial amount of product. Our product is only going to increase, our reactants are only going to decrease. The problem tells us we have 0.280 and 0.380 as our initial quantities. And then that's all we have besides our equilibrium constant. Since we need to have this row of information, we need to solve for this row, and right now we don't know anything about that row besides that it's going to be some change compared to what we have up here. We do know that we're going to change in a ratio that's predicted by the coefficients of our balanced chemical equation. So this is going to change by some amount to a rate of 1, some amount to a rate of 1, some amount to a rate of 2, and that some amount is just a number we don't know yet, so that's a variable. Most of the time we use x, so let's just call it x. These are all going to change by some amount x, but they're going to change compared to the mole ratio x. So then 0 plus 2x equals, of course, 2x. And then we could do 0.38 minus 1x, and we can solve that way. However, we are able to take a small liberty with our size of x because we know k is really, really small. Since k is really small, that means that the amount of product we make is very, very small, and most of what we have in our reaction is reactants. Because most of our final equilibrium container is reactants, this equilibrium value, initial compared to equilibrium, will barely change. So if k is small, times 10 to the negative fourth or smaller, negative fifth, negative sixth, etc., we don't have to actually change the initial concentration of our reactant. So I can just bring my initial straight down. Even though some of that reactant does change, statistically it's not going to be enough after significant figures to make a difference. So now I can just sub my numbers in. These are my equilibrium values into my equilibrium expression with my k value to get to the point of this. 4 times 10 to the negative fourth equals, we have 2x squared, 2x, the whole thing is squared. So 2x squared equals 4x squared over 0.28 times 0.38. Now, to solve for x, I'm going to need to move my denominator over to the other side of my equal sign, we do that by multiplying both sides. Same thing. Oops, 0.28, excuse me. Let me go ahead and erase that so that looks a little bit neater. This will of course cross off. So I'm left with 0.28 times 0.38 times 4 times 10 to the negative fourth equaling 4x squared. I need to solve for x. I need to divide by 4, and then I need to get just x, so I need to square root. So x equals this whole thing. Just make sure to use parentheses when you're solving for that. What you should find is that x equals 3.26 times 10 to the negative third. And that's great. The problem though asks what's the concentration of NO. Well, here's the concentration I want to know because it's the equilibrium value. Since this is 2x, I need to do this times 2. So I get 6.52 as my answer times 10 to the negative third. Sig figs, here's an initial measurement followed by an additional initial measurement. This actually isn't a sig fig provider because this is a constant value that can be found inside of a resource. So it's not a measured value. Therefore, we pull our sig figs from the measured values that are given to us in the problem. 3 sig figs is good, and since I'm looking for a concentration, I need a unit and a substance. Box that answer so you can find it. To summarize, write out your expression, fill in your ICE table, including the coefficients, because that's going to help us with our change values. You can always start out with 0, minus for reactants, plus for products. And then if K is really small, times 10 to the negative fourth or smaller, we don't have to change the concentration of our reactants. They will stay essentially the same. Thanks for watching. Good luck.